Okay, everyone, welcome to now the fifth lecture of this course on exponential asymptotics and for the physical sciences. The last few lectures, what we've been building up towards is to give you the necessary background material for asymptotics that you would typically hope to see in a first course on perturbation theory or asymptotic analysis. So we've gone through boundary layer theory, and then the last lecture we talked about integral approximations. We talked about integration by parts, and then also this method known as Laplace's method. So this lecture we're going to finish up with Laplace's method, and then we're going to introduce you to the most powerful of all the integral approximation methods, which is the method of steepest descents. And you can think of the method of steepest descents as a generalization of Laplace's method, where you're going to take advantage of the power of the complex plane and think about approximating integrals by deforming contours into the complex plane. Now, before that, I want to finish up with Laplace's method. So this is the integral that we talked about last time, where you're looking at approximating this integral for large, for the moment, positive values of x, just for ease of consideration. And we worked mainly through an example last time where the function phi, so if you think of your domain of integration from a to b, the function phi might look something like this. So the example we looked at, phi has a maximum on the left endpoint. And the idea is that as x grows to be larger and larger, the maxima of phi is increasingly exponentially dominant over any other location along the integration domain. So you would expect that this integral can be approximated in a little neighborhood about this point A. So you might take an approximation from a to a plus epsilon. And anywhere outside of this neighborhood, it's going to be exponentially subdominant from the approximation inside the neighborhood. You truncate the integral from a to b to a plus epsilon, and then you essentially Taylor expand each of the components and then attempt to approximate that resultant integral. One of the key steps that happens when you do this approximation is that when you truncate it from a to a plus epsilon, you then apply this trick where you can actually expand this right endpoint of integration all the way to infinity. And you can essentially do that because when you Taylor expand the integrand, the f and the phi components, you basically end up with a Gaussian in a lot of cases, and then it doesn't really matter if you extend it to infinity because you just introduce exponentially small errors. So that's one version of Laplace's method. And the other version of Laplace's method you would apply if your function phi looks something like this. So in this case, phi has a local maxima somewhere within the domain of integration. But the same philosophy applies. You take this integral, you truncate it in a little neighborhood from about the point C, and then you start expanding each of the functions, hoping to get something that's simpler to evaluate. You can have much more complicated functions phi. You can have multiple maxima, but the philosophy is largely the same. You find the largest maximum point. This gives you the dominant contributions. Other maxima will also produce subdominant contributions, and in more challenging problems, you might want to estimate those subdominant contributions. So we're going to do the example for this, this version of Laplace in the second picture, where you have the internal maximum. Okay, so let's call this case 2. And so it starts off largely the same. You're going to approximate I into an integral from a to c minus epsilon, and then from c minus epsilon to c plus epsilon, and then from c plus epsilon to b. And so you've basically split it up so that there's a little piece here from minus epsilon to plus epsilon. But the logic is largely the same, that outside of this interval, as long as epsilon is chosen sufficiently small, then outside of this interval, the contribution of the middle integral is going to exponentially dominate over the contributions from the first and the third integrals. So you can refer to the notes, which I have to upload the most updated version of the notes, but once I do so after today's lecture, you'll see there's an estimate that you can derive, which is if I call this 1, 2, and 3, then 1 and 3 will be much smaller than 2 as long as epsilon squared times x is much less than 1. So if x gets to be larger and larger, as long as this neighborhood scales like the 1 over the square root of x, you're okay. Okay? But in any case, you're now going to look at the integral 2. You're going to expand f and phi into the Taylor expansion about about the critical point C. And in that case, you're going to have a local integral from c minus epsilon to c plus epsilon. Let's expand f to be f prime f of c, then f prime of c. We're not actually going to need that, so I'll just write this as order. This is going to be t minus c, the linear terms. And then you have to expand the numerator, the exponential argument. And it's best to expand this into a few terms. The first derivative is going to be 0 because it's just a maxima point. And then so you're going to have the second derivative. So phi double prime of c, then t minus c squared over 2. And then you're going to have the cubic terms and higher. Okay, and then this is multiplied by dt. Okay, and basically the idea is that this one factors out. In fact, let's just do that here. This is going to be f of c factoring out here, and then I have a exponent x times phi of c, and then integral from c minus epsilon to c plus epsilon. And then is 1 times e to the phi double prime of c, and then this is t minus c squared over 2. This leaves you with a t minus c cubed over 3 factorial times x, which you can then Taylor expand about 0. So if I erase the picture here, okay, if I erase the picture, then I have 1 plus order, and then this would be x times t minus c cubed dt. So again, as long as I can make sure that this quantity remains small, which it must do because I'm integrating in a little epsilon neighborhood, so I'm going to have a condition where something like x times epsilon cubed has to be small, then I can do this Taylor expansion. And that's the Gaussian that you'll recognize there. Because it's a maxima, this second derivative of c is then negative, and then there's the typical Gaussian. Okay? So you can then make a judicious transformation here. So if you do, the kind of obvious one is to make this one look more and more like a Gaussian. So if I let s be root x times t minus c, then I'll start to get s squares. And sure, I'll go one extra step here. So this is then f of c e to the x times phi of c. I'll have a root x once I've made that coordinate transformation. This is a minus root x times epsilon. And then this is a plus root times x times epsilon. And then this is e to the s squared times phi double prime of c over 2. And then you have in brackets 1 plus dot dot dot. So this is order s cubed over root x. And then ds. Okay, so, and then at this point, you're going to do this trick that you can extend this domain all the way to minus infinity and positive infinity because everything here is just exponentially small outside of that domain, and you just introduce exponentially small errors. This becomes minus infinity to positive infinity, and then you can rescale this if you like, and then use the fact that you know the integral of the Gaussian from minus infinity to positive infinity. Okay, the final result, let's write that out. The final result is that this is then just twiddles. If you just want the leading order term, you'll have a root 2 pi, so that's from your root pi is the so the integral from minus infinity to infinity of e to the minus u squared du is root pi. So that's where, and then you have factors of 2 here, which becomes the square root of 2. And then multiply by f of c, multiplied by e to the x times phi of c, and then you have a denominator which is root of minus x times phi double prime of c. Okay, and we're assuming that this quantity is non-zero just for simplicity, and then this is negative so that everything turns out to be fine. If you want to, you can derive higher order terms from this, and you can kind of see what the procedure is if you do so. You just have to keep more and more terms and then integrate deeper and deeper in. And I think you can look up, I think in the notes, in the exercises, I should say the exercises are very incomplete. I kind of write the exercises, I write the notes, and I might have an idea of an exercise. But in other references, you can find the full expansion, the full required expansion of this kind of problem. Okay, but this is just giving you the leading order expansion as a function of the Taylor series coefficients, or the leading Taylor series behaviors. Now, this is basically it of Laplace's method. It's such a powerful idea. Before we go on, there was just a question in the chat. So someone had asked, I think, what if phi, I think they said psi, but I think it's phi. Phi is not continuous at some c. So remember, this is just, this is just a heuristic, right? So what I haven't done for you is I haven't given you the full limitation of the function. So I can say, okay, let's look at this function here. Let's consider f and phi to be continuous. Phi needs to be twice differentiable in order for us to get to this point here, right? But in your own research or in your own problems, you might have phi which is discontinuous at points within the interval, right? So your phi maybe doesn't look as nice as that. Maybe it's got some, that you're integrating from an A to a point B. But the underlying philosophy in these integral approximations remains exactly the same. You want to basically think that the dominant contribution to the integral comes from maxima, local maxima, and along the integral from A to B. There may be discontinuities, and if you saw this in an actual problem, you have to go to the integral and think real hard and think, well, is it actually integrable at that point? And then you may have to do a local asymptotic approximation to find out whether there is an important contribution from this point. So we're not covering all the possible cases of phi. There's going to be lots of different possible cases of phi and lots of different variations of this problem that range from being quite trivial variations to quite difficult variations. So for example, one variation, which is well known, is that sometimes the phi function is not going to be well behaved at certain points in the domain. And in order for you to put it into a form where when you can use Laplace's method, you may need to do integration by parts. You may need to hit it a few times with integration by parts to get it into a form where you can then apply this kind of theorem, right? But the truth is that most of the time, I mean, in a lot of your own research problems, you wouldn't just apply this formula without thinking. You have to think real hard about how I'm going to split the domain into the relevant parts. And there may be versions of this theorem which you're going to have to develop and use dependent on what your function looks like. But the philosophy is essentially when x is large, this exponential factor is so overbearing that most of the dominant contributions are going to come from the maxima of phi. So this is a nice segue into the method of steepest ascents. And the method of steepest descent is kind of like the full generalization of Laplace's method. Okay, and it's not just a method. It's kind of in essence a philosophy of how you evaluate integrals in general. Okay, let me do an example because I've got a little bit of time. Let's just do an example of Laplace's method before we go on. I shouldn't have erased that formula because I'm going to need it in a minute. But let's look at this integral and get one of the most famous results from asymptotics, which is Stirling's formula. So I want to evaluate the asymptotics of this integral here, t to the x e to the minus t dt, as x goes to infinity for large values of that argument. Okay, so the first thing when you look at this thing is you have to think real hard about what to do with this power because you're not used to seeing t to the x. And here x is quite large, and the trick is just to put this firstly into an exponential form. So you can write this as e to the x log t minus t dt. Okay, so now that looks a bit more familiar. Now, there's another problem of applying Laplace's method to this problem, which is that if so it's not quite in the form that I'm expecting, right? So usually I think of this as my phi function. This is phi of t, and I don't worry about the prefactor here of e to the minus t. But this e to the minus t is going to cause us a little bit of difficulty. So let me just naively set phi. I'm going to look at phi of x and t. So that's x log t minus t. And I'm just going to think of the maxima of that as a function of t, right? So phi t is then x over t minus 1. Okay. And so therefore, for each given value of x, that has a maxima when t is equal to x. So this problem is slightly annoying because essentially for every value of x, your maxima is moving with x. Okay, so that's what's known as a movable maxima problem. And the essence of this is that the order of your prefactor, which is the f of t, is actually exponential. It screws up the ordering. But there's a trick around this, is you can just make a coordinate substitution to this function here, which puts it into the usual form of Laplace's method. Okay, so so I can write this. Let me see if I can find the substitution. So I'm going to let t be x of tau, which essentially makes this t then. It gives me a factor of x here, and I can use logarithms to expand as log of tau. And having done so, this allows me to write this integral as x to the x plus 1, the integral from 0 to infinity of e to the x times phi of tau. So this is now in our more traditional form, okay? And then phi of tau is just minus tau plus log tau. Okay, fine. All right. So I'm brushing over these kind of movable maxima problems, but they're kind of the point is that in a variety of problems, you may have to do a transformation, especially for these kinds of problems where the prefactor is exponential in t, to put it into the required form where you can then use Laplace's method. But now that you have, it's very straightforward. If you look at what the graph of phi of t looks like, it essentially goes to minus infinity as tau goes to 0. And then it's linear with a gradient of minus tau as tau goes to infinity. And it has a maxima at this point. So that means that the dominant contribution of this integral you'd expect to be localized around this maximum. Where is it? Well, phi prime of tau is just minus 1 plus 1 over tau is equal to 0 if tau is equal to 1. And you can then calculate what phi of 1 is. Okay, and that's just minus 1. And you can also calculate what phi double prime of 1 is, and that's just minus 1. So it is a maxima. Okay, and at this stage, it's literally as simple as putting into the formula. So the formula tells you that the gamma function of x plus 1 to this order of approximation is root 2 pi, and then it's f of c, but in this case, the f is just 1. It's f of c times, I'm missing a factor of x to the x plus 1 here, so I have x to the x plus 1. And then I have e to the x times phi of c, so that gets me a minus 1. And then I have a root minus x times the second derivative, so that gets me a minus 1 there. And so this is essentially root 2 pi times x to the x plus a half times e to the minus x. And this, if x is a integer, a positive integer, is essentially Stirling's formula. So we've just derived it, as long as you have the integral to start off with. You can see how straightforward it is applying this rule. But in this case, the function is very well behaved. It just peaks at this point, and then it's exponentially smaller on the initial bit and the end bit. Okay? So this is Laplace's method. And we've looked at the version where you have the dominant contribution coming from the endpoints, and we looked at the version where the dominant contribution comes from the middle point. Okay. So now we're ready to talk about the most complicated of all the methods, which is the method of steepest ascents. Okay. Now I'm going to the method of steepest ascents, because we're going to want to be using complex numbers. I want to make a little bit of a notation shift, and instead of using x's for my large parameter, I'm going to do an annoying thing and use lambdas instead, because I want to use x's for the real part of a complex a variable. Okay, so we're going to look at very similar looking integrals, I of lambda. We're going to consider this to be a very general kind of integral. So it's going to be a 1D integral. C is going to be somewhere in the complex plane, but the version that we were looking at is just along the real axis, and it can be that as well. And then I have a prefactor f of t, e to the lambda, and I'm going to call this h of t dt. So I'm just switch my phi to h's instead. And okay, I want to look at when lambda goes to infinity. Okay, just for simplicity, though it doesn't really matter, it just helps us that we don't have to think about it. Lambda here is positive. You can extend all these methods to if lambda is large and complex as well, right? So it can be negative or it can be complex. And remember that we're trying to teach you the philosophy of how to do this rather than the recipe. F and h here are, they're going to be complex functions or real valued functions as well, which are also complex functions. They're going to be so they're going to be analytic in the complex plane. So t in C, and except at critical points, isolated points. put that in brackets because so basically f and h can have things like they can be logs, they can be t to the 1/2, they can have branch points, or they can be completely smooth as well, completely analytic everywhere in the complex plane. Okay. And of course, just as that question came up about, can you use Laplace's method for functions with discontinuities, we can make f and h even more pathological, and the philosophy is still going to hold. It's going to tell us how to think about where the dominant contributions are coming from, even though you might have some very specific modifications you need to do to the method. Okay? And C is our contour contour in the complex plane. Okay, but C can run along the real axis. It can be going from -infinity to positive infinity. It can go from 0 to infinity. It can be a contour with lots of spirals or whatever you like. So it can be something quite unique. Okay, so how do we think about doing this kind of problem? Other than, right now it's just a neat generalization, but actually you're going to see that this is going to tie together all the methods we've learned so far. Let's think of h of t, and let's write that. I'm going to, t is my integration variable, but just for familiarity's sake, I'm going to write h of z for z to be a complex number. And I'm going to split that into its real and imaginary parts, and so I'll write that as phi of z plus I times psi of z. Okay, and if you like, you can think of this as if you want to write the real and imaginary parts in that way, you can do so. And think of z as x plus iy. Okay, so for the first bit, we kind of want to try to use what we've learned about Laplace's method and apply it to this integral, but now this h function might be complex valued, and just see what happens. Well, I can certainly bound it, so I can look at I of lambda, right? And that has to be less than or equal to the integral of just the absolute value of t. And because e to the lambda I times psi is just creating an oscillation, a cosine or a sine, then I can bound that just by the real part of h. So this gets me lambda of phi of t dt. Okay, so just for simplicity, let's take this between a point, let's say ta and a tb. But of course, the ta and tb can also be infinity as well, right? As long as your function is integrable. And there's lots of examples that we're going to want to think about where the endpoint of integration is also infinity. So let's look at a picture. Let's look at a picture of what we might be considering. So here is our integration variable t, but we're now thinking of t in the complex plane. So we might take our contour to be starting from 0, and then maybe it does whatever it does, and it goes to infinity. So that might be our contour c, and this is the imaginary part of t. I've gone a bit creative here and taken it to be some kind of thing, but the previous version is just from 0 to infinity. Okay. Now, this thing here has to be less than L, the length of the curve, times the maximum over that curve of the argument. I mean, essentially, this is the worst it can be. I guess I should take a mod here. So I just replace every point by the maximum of phi along that value, right? And by Cauchy's theorem, I'm allowed to deform this contour however I like, as long as I don't shift the endpoints of integration. If I keep this one pinned at 0 and keep this one pinned at positive infinity along this direction, then I might find, let's say, a value somewhere in the complex plane where this phi is the biggest. And in that case, I can feel free to deform my contour through that point and not change its value, as long as I don't pass through any singularities or anything like that. So I can take my piece of string here from 0 to infinity and then just deform it through a value that I suspect is going to exist, this t naught, where phi is maximal. So this sounds very good, and this is essentially Laplace's method. And so you might think, if you go with this philosophy, that maybe I can then just approximate this as root 2 pi times, right, what was our previous formula? It was this thing here, but let's say instead of x's I have lambdas now. I'm just going to approximate it by its value, this minus lambda, and then h double prime of t naught. So you're just kind of using the same idea as you did previously. You're going to deform into a local contribution around your maximum point, and then just kind of crank the handle and apply Laplace's method. So that sounds very good. But there's a bit of a problem. And the problem is that if you look at the phase of this approximation, well, the first problem is if you actually try this, this thing ends up being much larger than what the actual contribution turns out to be. So it doesn't seem to work. And the problem is that if you look at the phase that we ignored, the phase is e to the I times lambda times psi of t. Well, we said this is bounded by magnitude 1, which is true, but if lambda is really large, then this thing is highly oscillatory along some path in the complex plane. It's oscillating very rapidly. And so if you're actually trying to approximate this integral and you're multiplying it by a function, which though bounded by minus 1 and 1 is oscillatory, then there's actually a lot of plus and minus cancellation that you've not considered in your approximation. So this seems to complicate the method that you're suggesting. But how do you get around that? Well, what if you were to take a path where phi of t is actually constant? So if you take a path where phi of t is constant, for example, you might take it to be the exact value of psi at that point, then this thing can be just removed from the integral, and then you no longer have a component which is highly oscillating in t. So that trick seems to work. And then now it's going to boil down to using Laplace's method. So what the punchline is moving towards is that, yes, you're allowed to take your contour, your original contour of integration from 0 to infinity, you're allowed to deform it through a key point, a key critical point, where the real part of that function is maximized, but you have to make sure that you move in the right direction. When you integrate through this point, you have lots of directions you can possibly choose from. You need to choose a direction where this is not oscillating, or rather the psi function is constant. And so the next part is we want to understand in the complex variable language, what are the implications if we were to do this? If I choose a path where psi is constant, what does that mean? Okay, and that boils down to some basic, quote unquote, basic complex and real analysis. It's just what it means to be a gradient, and what do I know about the real and complex parts of a function. Okay, so let's do that now. Let's just do some bullet points of what do we know about complex functions. So h of t, or h of z, remember, splits into a phi of z. Let me write that in here, so that's going to be split into a phi plus I times phi, the real and complex components of h. And I know that I have the Cauchy-Riemann equations. So any function, any analytic function h at a point of analyticity has to satisfy, what is that? I have phi x, the partial derivative d phi dx is d psi dy, and I have the partial derivative d phi dy is minus d psi dx. Okay? Okay, so now I have to ask myself, what happens if I have a maxima, right? So I'm going to assume that I have a local stationary point, so that phi x and phi y is 0. That's what I want to expand about. This is my point z0 or t0 there. And so if I have these two equalities, then I have the same thing with psi. Okay? All right. So at any point where I have a stationary point in phi, I also have a stationary point in psi. Okay? The next property I have is that if I think of the derivative dh dz, the complex derivative, then just by first principles, you can evaluate this by taking the partial derivative of the real and complex parts. And then if you like, you can apply your Cauchy-Riemann equations and switch this around here. So this is d psi dx minus I d psi dy d phi dy if I like. But in any case, the point is that if you have a point which is an extrema of phi and psi, then it must be also an extrema for this complex function of z, right? So this tells you that h prime at z0 is equal to 0 if these extrema relations hold at z0 is equal to x0 plus I y0. Okay? So the point is that these extrema that you're interested in, it's also an extrema for h. You have to look at where the derivative of h is 0. Okay, fine. The next thing we need to know a little bit about directions of steepest descent and ascent and how that relates to complex functions. So I can take my Cauchy-Riemann equations and I can prove that the gradient of phi dot the gradient of psi is 0. All right? So this tells me that the curves, this is the key thing, this is curves of constant psi are perpendicular to curves of constant phi. Okay. The other thing we know from vector calculus is that the gradient of phi is essentially the direction of steepest descent. So if you have a surface where the height of that surface is 5xy and you take the gradient of that function, that's a vector in the plane that just points in the direction of steepest descent or ascent, depending how you think about it. Right? And so therefore, the key thing, the one conclusion you're moving towards is that curves of constant psi are along directions of steepest descent or ascent. So we want to deform the contour into an appropriate direction here, which will have psi being constant for the reason that we pointed out before, so that you don't have this oscillation problems. And if you were to do that, you're actually lying along curves of steepest descent or ascent. Okay? So that's basically the last thing we need for this. And this is going to be clarified now with a picture. I'm going to try to draw you a picture. We're going to look at a function, h of z or h of t, and then we're going to start drawing some pictures of different curves of constant phase, of constant psi, and curves of steepest descent or ascent. And then we're going to see how it's all going to work. Okay. Now, before I do this, let me just write down the example, a toy example for us to work off of, so that we're talking about something a little bit more concrete. Okay, so let's consider, I want to do the asymptotics of the following problem. I want to estimate 1 over gamma function of lambda, and I'm not going to show you how to do this, but you can refer to the notes. But this can be written in the following form: 1 over 2 pi I times x to the x minus 1 times an integral over c of e to the lambda times h of s ds. Okay, and this h of s is s minus log s. Looks very familiar to the example we did before. The difference is that this contour C is no longer going to be along the real axis, but this contour C is what's called the Hankel contour. So if I imagine the real S, imaginary S plane, okay, firstly, 0 is a problem here. It's got a branch point at s equal to 0, and if you remember some of your complex analysis, you have to cut the plane along the negative real axis, that you're not allowed to travel across this cut unless you think real hard. But the contour C is what's known as a Hankel contour. It's basically just a contour that goes from minus infinity on the left and slightly below the axis to minus infinity, all the way back to minus infinity, but above the axis. And the value here is different from the value there because the log function has this branch cut, so you don't get 0 otherwise. Okay? So it turns out that you can define the gamma function in this way. As this contour C, we're not going to show you how that's done, but it's almost by an integral transform definition, but we now want to estimate the value of this integral. Okay? And we want to do that basically through this trick of deforming it through paths of steepest descent, where we can then locally approximate the integral about this key point. And as we kind of imagine, this key point is near the saddle point or near the maxima of this function, so we can take the derivative here, and it turns out to be at 1. So we're going to have to deform through 1. Okay? But before we do all that business, I want to just study the contours of that function, and then I want to explain how those contours relate to the integral approximation. Okay, so to develop the contours of this function, by the way, you can just go to any graphics program. You can do it in MATLAB or Mathematica or Python, and you're essentially just looking at the contours of the real and imaginary parts of that function. Right? So remember that psi is given by the imaginary part of h of s, and so you might think of h of sx plus I sy. Or if you like, hopefully, yeah, I don't want to use an x, and this is a lambda. Sorry, this is a lambda minus 1. Yeah, so let's use x and y's instead. Let's just for simplicity. That's also why I converted to using lambdas instead of x's and y's. And remember that the function, so psi is the function that you want to make sure is constant along the directions that you want to take. And then phi is the function that determines basically the exponential argument, how big that exponential is. And so in that case, that's just the real part of h of x plus iy. And in Mathematica, it's as simple as doing something like contour plot. And then you can essentially just take the imaginary part of this function that you define, and then you just give it in little arguments here that your x should run from, say, -2 to 2, and then your y runs from -2 to 2, say. So you can just put this kind of command into Mathematica. The alternative is that if you go to MATLAB or Python, you can just generate a mesh of values in x and y, and then just plot where the contours are. Okay? And if I plot those contours, I'm going to draw for you, at least schematically, what the picture looks like. Okay, so I've got my real axis here. I've called this x and y. Let me just move this over to the right here, so it's not in the light. A bit hard to see there. Okay, and there's a branch cut here. Okay, so basically at this point 1, I'm going to draw my curves of constant psi being in black. And there's essentially a curve of constant psi that looks like this. Okay, and I'll truncate my axis here. And then there's another curve of constant psi. Okay, so this is psi constant. And the value of the constant is in fact just the imaginary part of h of 1. And then this is also constant. And in addition to that, you have the real part of psi, of phi, which I'll draw in dashed. And away from this critical point, the real part of phi is intersecting the solid contours perpendicularly. That's kind of what it looks like, okay? Yeah. Okay. The second thing you'll notice by examining the contour plot, I should have printed this out, by the way. It would have been a lot easier if I showed you on the screen, but I'm going to do it by hand here. The second thing you'll notice is that over here, that's a valley and a valley. And in a valley, my phi is going to -infinity. So basically, the shape of the phi function over here and over here is low, right? Phi is going to -infinity, which you know that you need to have because if it didn't go to -infinity, it would not be integrable, right? And your original contour of integration goes from down here to up there, so that's good. Okay, and then what you'll notice if you examine the contours here is that basically the value of phi increases in that direction, and phi increases in that direction as well. Okay, but then going up in this direction, so the dashed lines as well will intersect perpendicularly. Remember, that's the rule, away from critical points. If I move up in that direction, phi decreases. And as I move down in that direction, phi decreases. Okay? And there's a special point here that we're not going to talk about at 0 where some stuff happens. But we don't need to know that. Okay? So this is essentially a result from kind of elementary complex and real analysis, which is at this special point where the first derivative of phi is 0 and psi is 0, because of the properties of phi and psi being the real and imaginary parts of a complex function, they have to be harmonic. And then if you go and look up some of the consequences of that, there's a maximum modulus theorem that essentially says that this cannot be a maximum along all possible paths of the function. So essentially this is a saddle point. And I'll draw for you what the surface looks like now, and hopefully that will make sense. So if I plot the surface for phi, then I know that as I walk through phi from left to right along this line, it's increasing. So it has to look like that. Okay, so I'm going to plot phi of x and y, which is the real part of the function. But I know that if I go from down to up, then it's descending, right? So it has to look like that. And that's your classic saddle point. Okay, so the surface for phi looks essentially like this. It's got the direction of steepest descent going down and then steepest ascent going up. But going in this direction is steepest ascent and then descent going down. And as we said to you before, if you deform along the solid line where psi is stationary, psi is constant, then along these lines, phi is descending or ascending maximally. Okay? So basically, now you have an intuition of how you're supposed to do this deformation problem. Basically, your contour C starts off at minus infinity here. It does whatever it needs to do to get back to minus infinity up there. By Cauchy's theorem, you're always allowed to deform this into paths of steepest descent or ascent, or along any other path. But if you deform it and attach yourself to this curve and come back to infinity along that curve there, then along this curve, psi is constant. Your phase is not changing. It's not rapidly oscillating. So now you get to use Laplace's method at this point. Phi is just going from minus infinity, going up to a maximum, and going back down to minus infinity. And so the dominant contribution to this integral has to come from this one point. And that's the trick. Right? That's the method of steepest descent in a nutshell. Okay? So the basic philosophy of the method of steepest descent is as follows. I give you an integral somewhere in the complex plane, or it can be along the real line, and then you deform it in the complex plane to make use of this trick. You first look at the saddle points of h, and you figure out, either by plotting on a computer or by thinking real hard, what the contours look like for this h function. In particular, you're looking at paths of steepest descent or ascent, or paths where the imaginary part of h is constant. Once you've found those paths, you're looking to go from a start point to an end point, deform along those paths, and pick up critical points which correspond to saddle points in the function. Once you've done that, then you do a local expansion. You just have to do a local expansion, truncate that curve about that point, make sure you're moving vertically upwards in this case. If you don't move in the right way, you're not going to get the right answer because you're always going to have that oscillation. And then the integration of that turns out to be super simple, okay? At least a leading order. So let me, in what time remains, let me just show you how that's done for this problem, and then you'll see that actually, once you understand how to perform the deformation, it turns out to be very simple. Okay, so for this function, h of s, h prime of s is just 1 minus 1 over s is equal to 0, so that tells me my saddle point's at 1, okay, which I kind of knew that already. Okay, now I can do the, okay, so let me now rewrite this integral. Okay, I know that h of s, I can go and Taylor expand that near the critical point. So this is basically 1 plus s minus 1 squared over 2 minus s minus 1 cubed over 3. Okay, and at s is equal to 1, you don't have a first derivative. And notice our little Gaussian friend there, which always seems to crop up. And if you put that into the integral, then the integral gets the following form. It's e to the x over 2 pi I x to the x minus 1. I'm sorry, every time there's an x, it should rather be lambda. I need to correct that in the notes. It is lambda to the lambda minus 1, lambda to the 1/2, times an integral over, we're going to do an integral over c of e to the u squared over 2, and I had to do a little transformation here of 1 plus dot 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 du, and I had to do a little transformation for u in the usual way. I'm going to let x times s minus 1 squared be u squared. Okay? And the point is now I'm integrating complex u, and in order for this to become a Gaussian, I want it to be basically I times v, right? Because then I get my Gaussian, which is telling you that the path that you're supposed to take is along a vertical line, which is what I explained to you before. Okay? So you can then, now the other way for you to figure out what the path of integration should be is that you just look at this local function of h. You say h is, let's say, x plus iy, right? And the imaginary, and if I expand that, I get 1 plus, and then this is a u squared minus v squared, sorry, x squared minus y squared. I have plus 2ixy all over 2 plus dot dot dot. And so locally, near the relevant point, sorry, I'm being a little bit quick here. I want to let s minus 1 be x plus iy. I understand it's a bit confusing. I then make this into an x plus iy squared. And the point is that this thing here will have the imaginary part of h being constant along x equal to 0. So it's along this point 1. And that's why the local path of steepest descent has to move upwards. Okay? So I've covered this a little bit quickly, but hopefully you understand the intuition. You have different ways of determining this path of steepest descent or ascent. You can do it kind of by inspection of this guy and say, well, obviously if I let u be I times v, I get a nice Gaussian. That's nice. You can do it by analyzing the properties of this h function and looking at the real and complex parts. Or you can even do it graphically just by plotting the contours and then getting an intuition then. Okay? So now I then just have to set the answer is that I'll just have to let u is equal to I times v, and then now you see this becomes a Gaussian. I extend my integration contour from minus infinity, from a little neighborhood around this point to minus infinity and positive infinity, and I get my usual Gaussian function, and then it's all going to come out. You're going to predict essentially that 1 over the gamma function of lambda is basically e to the lambda over 2 pi lambda to the lambda minus 1/2, an integral from minus infinity to positive infinity of e to the minus v squared over 2 dv. And then this becomes your root pi over 2, or 2 root pi, no, one or the other. And then you end up with the usual formula. If you invert the function, you'll recognize the gamma function expansion that we found before. Okay? So this is basically all I'm going to say about steepest descents. We're actually going to come and get a lot more practice with steepest descents in the next few lectures, because we're going to be we're going to eventually now come back to this topic of exponential asymptotics. We're going to do some examples of exponential asymptotics where we're going to need steepest descents. okay, involving things like the analysis of the exponential integral or the analysis of the area function, etc. But the philosophy, let's just recap the philosophy, which is that you have an integral with a parameter which is going to infinity or 0, and you then look at what's happening with the integration, with the integrand function in the complex plane. The fact that your parameter goes to infinity tells you that points where the argument of that exponential is maximized is really important. So it's advantageous for you to deform your contour through such points. But you have an issue, which is that because it's a complex function, it has a phase argument, and therefore it's advantageous for you to deform along paths of constant phase, of constant psi. It turns out that if you're to do that, if you deform along paths of constant psi, this happens to be exactly the directions of steepest descent or ascent. And that's why this is called the method of steepest descents. Okay? Now, if I gave you a contour C, which had finite points of integration, so let's say my contour went from A to B, there's my C, along the real axis, then again, what you're going to have to do is to deform this into the relevant paths of steepest descent and ascent. There may be critical points that you want to pass through. Let's call this T0. And then what you do is you consider a local neighborhood of this point and derive the asymptotic contribution. But in addition to the neighborhood of T0, you may need to also, just as you do with Laplace's method, you may have to include the contributions from the endpoints as well, because these may actually be of a higher height than this T0. And so actually it might be A or B which is producing the dominant contributions. Okay? And if you pass through multiple critical points, saddle points, you should also include those ones as well. But actually, if you just want the leading contribution, you just need to figure out what's the point that contributes the largest to that integral. And that is a subtlety which is actually going to be involved in our discussion with the exponential asymptotics. Okay, so this is it. This is the last review session. This is the crash course on asymptotics. We finish integral approximations with the method of steepest descents. And then in the next lecture, we're now going to go back to studying what is exponential asymptotics, what's some simple examples with exponential asymptotics. We're going to look at how these questions of integral approximations relate to that issue. Thank you, and I'll see you next time.